Okay.
So there's n minus 1 Cauchy-Riemann vector Cauchy-Riemann equations, or n squared minus n scalar Cauchy-Riemann equations.
Okay, so do you think we could say that, so we have, if the Cauchys for GZ hold, if we call this next derivative, whatever, what do you want to call the partial f, partial w?
Oh, right, well, I guess,
Like, can you think, do you think we would be able to marry them? Like both the Cauchys or both?
well, one other thought before we move on from here is that it might be useful, I mean, just thought experiment for a second here, but we can also write the symmetric ones down, right? Like, if you have partial g, partial x, 1, I, star vj, you could write that as vi star partial g, partial x, 1j. That's an alternative characterization we could use for distinct I and j. This would be helpful if we're working in a context where we don't want to let v1 be the identity for the algebra. Now, I'm just pointing that out here. I think I'm going to stick with what's written in black for the time being. Now, you're going back to your question, what about the w derivative? I don't know, we could call the other thing h, you know,
Okay.
for the sake of discussion at the moment. Say h of w is f of z naught, comma w.
I'm calling it partial h, partial x2i, right?
Yeah, exactly. So it's a partial h, partial x, you said 2i?
Yeah.
Perfect.
Is, yeah, would you say, yeah.
Partial h, partial x, 2, 1,
Yeah.
star vi. Like, those would be the Cauchy-Riemann equations. So I mean, these h's and g's, they're half frozen functions or something, right? They're like the thawed Cauchy-Riemann equations. I don't know. You could write these out more explicitly.
So if we took a partial h of partial x2i at a point and then differentiated, well, no, we can't.
No, I will say, right? I'm going to go back up to my jibber jabber up here. Now, remember, I erased it at this point, but you remember before I talked about the fact that the differential.
Before you do that, okay, so we know that I had an idea. I don't know if it's so if we do that, and that, you could say is this.
Let me fix this equation here.
Okay. And then you could say this. Okay, you said, I'm saying VI, so this would be VJ. You might have to clean this up because I think I'm doing my notation off, but partial h, and then that'd be partial x2, so if this is I, and that's j, So yeah, that's what we had. So this would be J. We could change this for I, this, H, X, 2, I, and then we flip, and this would be J, and then I think,
Are you writing down the symmetric ones for H?
yeah, but that's, if I remember okay. I'm calling back to like one of the first lectures we had.
Uh-huh.
I could be completely wrong about this. So, so we start with that. Where was I? I might be getting some of my notation wrong. And then if it's a calculus and right linear, this means you could do this, right? For
But VI is a basis thing, so like, I mean basis element, I don't know what DDW of VI means. I mean it would be 0, I would think, but so you're trying to DDW of
yeah, see, my point is here, if you could apply the same rule, if you could apply this rule to that. But I don't know what this DDW would be. Because like if you could apply this same rule, you know, you VJ of, I don't think this is going to work anyway, but see,
oh, we can look at that next.
yeah, let's see.
Thing is, I would start with, and maybe you are in some sense, but I would start with like partial squared f, partial z, partial w, or whatever.
Yeah. I don't see how this is going to commute no matter what.
Huh.
I was trying to see if you could use these rules to make it commute, but yeah, I get stuck here. I don't know what you could do for here. Flip that.
So your partial h, partial 2, 1, is that h is?
I was trying to copy notation over here. I might have got messed up somewhere.
Well, partial h, partial 2, 1 is. That is what I would think of as partial h, partial w. So
Yeah.
what you really want to be understanding is not this. Whoop. I mean, we're going to be after essentially kind of like
yeah.
that's what we're going to be after. And so the thing is, this, if it exists, well, to say it another way, this existing is tantamount to partial x11 of
Yeah.
this stuff.
Mhm.
That. So
I was trying to rewrite this as that. and then write this,
So
this thing,
let's,
that thing, because
so
we have a
this-
rule.
I mean, it really is just this though. I mean,
Yeah,
this is not it.
yeah,
What I'm trying to say is this is part of it, but in order for this to actually imply that algebra derivatives exist, we need not just this, but also that a whole slew of Cauchy-Riemann equations are satisfied. But this, if we go back to the real theory, we can do the real partial derivatives,
yeah.
so you can flip those. But it's not, see, the thing is,
Well, I was trying to use that one thing that we had as, like doing this thing, but I think you're right with that variable, with the basis thing. I was trying to do it even if I was trying to see if there was a possible like, if you could somehow commute them without even knowing if they were real, functions. Like the underlying real part. Because if it's real, you can commute them, but like, if you could say that you could do this without, I feel like
it's been a few years since I proved that the derivative commuting rule, I did it once in advanced calculus, and then I didn't do it after that, because it's kind of a little bit technical, and it's not good for lecture, but let's come back to this in a minute. I mean, I think that's I think you got the right general idea. Where's my, oh, thanks.
I'm sitting on it.
It's all good. But that thing I'm just erasing here, like that's not enough, because you need, for the partial derivative to exist, you need like this, so for this partial derivative to exist, this derivative of that function has to exist. The derivative of that function exists only if like there's like a bunch of Cauchy-Riemann equations are true. Likewise, this only exists if a bunch of Cauchy-Riemann equations are true. So if those Cauchy-Riemann equations are true, then well, I have to think through it. Sorry, we stop trying to. I just a bunch of stuff I got right. Now this here though is easier. See, because suppose that this is a function for which, suppose partial f, partial z, and partial f, partial w exist as described down here, right? And also let us not write the point at which they exist, because it's a drag to write that. But if they exist at some point, obviously, or some family of points, then that is tantamount to assuming that the Cauchy-Riemann equations hold for the real partial derivatives, right? So, like partial f x1, 2 and partial f, these guys I can replace with what? Like partial f, partial x1, 1 again, right?
Yeah.
But this time times v2. Partial f x1, 1 again, yeah? Times vn. And over here, same song and dance, but the numeration gets a little twisted. So partial x, well, x2, 1 actually, right? Fine. Oh, I guess I'm just writing that. The x2, 1 plus partial f, partial x2, 2 star v2 dx2, 2. Finally, partial f, partial x. Not 2, 2, 2, 1. It's always 2, 1 on these. 2, 1 star vn dx 2n. So just to point out, so given all those Cauchy-Riemann equations, right, you can factor out partial f, partial x1, 1 times what? Times this dx1, 1 plus, v2 dx. I guess you could write a star here, just to stick with this, notation. If you want to preserve the number of stars in the equation, stupid. But the point is, they all have partial x, the blue terms, and they all have partial x, 2, 1, the pink terms here, yeah?
Mm-hmm.
And also, it is consistent. Is that your phone? Am I imagining things?
Was it my phone?
What?
No, not my phone.
What's it? Missed call. 1-508-952. Take a while. Shot in the dark and say it's about my extended car warranty. All right, so so this right here, actually, if you think about z as being x11 plus x12 v2 plus x1n vn, and if you think about this one as being w, if you recognize z and w are so defined, right, and you think about taking the differential of those, algebra value differential, well, what we have above is literally dz. What we have above over there, it's literally dw. So you see what we have in the case that, I guess I should just erase from the start, by the way, because I'm not really sticking with this, am I? So what do we have? We have partial f, partial x11, and what is partial f, partial x11? Partial f, partial x11 is partial f, partial z. By the way, that is exactly partial f, partial z.
Oh yeah, that's what we defined, yeah.
So, and then you can write the star dz, or, eventually I'll omit the stars, and then you have partial f, partial w, star dw. Or you could just write partial f, partial z. I don't know, stars, no stars, whatever, but. So, what I'm getting at here is, if we do a calculus right, then the differential of the function, you won't need to do all of the underlying real things. Like once you get through it, you'll be able to take the differential at the level of the algebra notation. So this is the sort of thing I was looking for, is because if it was always just all the real underlying stuff, then it wouldn't be interesting. The fact that, we get back to the same kind of formulas that we had in the real case, but with replacing real derivatives with algebra derivatives, that's, part of the game. All right. So, then the next question is, and I think by the way, so essentially I I have erased it, but remember over here I said you could express the differential as, I mean, for an arbitrary function that's not, say, differentiable with, and so we should maybe say that this is differentiable with respect to the first component, differentiable with the second component, something like that. So if a function is not a differentiable with respect to its components, then generally, like the differential, you could express as, I mean, it would have these two pieces, but it would also have, you know, it would have all the other pieces that come from the conjugate differentials for what it's worth. But anyway, this is what we're interested in, is when this does happen. So if this does happen, it's great. And all right. So I guess the next question is, can we? I mean, we still haven't. So we're just focusing on the forward direction at the moment. The reverse direction is what's going to be more challenging.
Given, yeah.
Okay, so let's take a stab at the. Give us our. Let's take our. What's the word here? Let me take a first stab at the commuting partial derivative problem. So let's suppose that partial f partial z and partial f partial w both exist, and f is twice continuously differentiable. All right, but what I really want there is just that the function f has met the condition for the real partial derivatives to commute. Now, once we take a break here, I'll go try to find my copy of Advanced Calculus, the Advanced Calculus book that I have, and I'll try to make sure that we're not neglecting something. There may be some kind of I don't think there's a. I think this is a local result. I don't think we need any kind of global nuanced topological condition on the domain in which it holds. All right, so anyway, here we go. So what we want to look at is partial squared f, partial z, partial w, right? So this is partial z of partial f, partial w, all right? But partial f, partial w is what?
Partial f partial w is d dw f z naught. Oh wait, are we going over here?
Yeah, we're gonna suppress the point for this is the first draft, so I'm gonna be a little bit nutshell. I always, typically in proof like this, I'll go through like a sloppy version, and then I'll like add the point and try to make sure I'm not like deceiving myself, you know. But that's partial. If this exists, then that, in terms of the underlying real derivatives, is partial f, partial x21 in our current enumeration of where the unit is and everything. Assuming v1 is the unit for the algebra. And this is the matching coordinate in A cross A, the second component. All right, so I see now that to make progress here, I need a differentiability of partial f, partial z, right? Partial w, rather. Because, well, for one thing, you know, for this, And I need A differentiability, partial F, partial W in the first slot. I'll say in the Z direction, in Z component, since that's without ambiguity. But it's really in the first slot, you know? And if I have that, right? If I have that, then what this means is partial differentiation with respect to the 1-1 component. I'm assuming, of course, again, that this Z derivative exists. And now, I remember I've assumed that F is twice continuously differentiable. So these, then by the usual theorem of real analysis, I can commute the partials. And, all right, so this, of course, is partial F, partial Z, right? So, of course, now I need A differentiability of partial F, partial Z in the W component. In order for this real derivative to be understood as partial W of partial F, partial Z, right? But this is kind of a template for the argument. It's kind of funny that I didn't actually have to explicitly use the Cauchy-Riemann equations. They're kind of buried in these comments, I think. So I guess the conditions we need here. So we need twice, like the repeated A differentiability in,
Did we ever go over what?
we need the A derivatives, partial A derivatives up to second order to both to exist for the function. If that's the case, then I think we have partial squared F, partial Z, partial W is equal to partial squared F, partial W, partial Z.
So, right here my definitions on A to A for differentiability, but do we ever state what we mean from differentiability from A cross A into A?
That's what this was.
Okay.
And there might be a better, might be even a better way to define it than what I have done over there, but I'm cautiously optimistic that this proof is going to stand up to further scrutiny. Although I will say, we also have previously, I think that actually the condition of twice A differentiable won't be needed because we have a theorem from back in the A differentiable paper, the first one, that if you have a function which is twice real differentiable, continuously so, and you have the derivative, if it's once A differentiable, that implies twice a differentiable, because like, in fact, if the function's smooth and one a derivative exists, it follows, in fact, that all a derivatives, all higher a derivatives must exist. That's something I've proved before. So I think that the condition that the a derivative, these extra conditions I was writing off to the side here, that partial f, partial w, and partial f, partial z exist, they're like, they're for free if we just know that the function is twice continuously differentiable in the real sense, and once a differentiable, like that will suffice. Pedagogically, I guess you could, say, well, okay, well then you're still not wrong to assume partial f, partial w, and partial f, partial z exist. I mean, they have to, but sometimes we try to state theorems with a minimal set of preconditions, and those may not be actually needed. Should I go back to why once a differentiable implies twice a differentiable?
I have that written down somewhere.
Yeah.
Wait, does it hold for like a cross a and a2, like that same theorem?
I suspect so.
Okay. But yeah, I have that. I have
But
that
you're, I mean, that's the question: is does the argument there follow here? And these, I think we could write definitions of the. We could express this in terms of right linearity. That might be useful, actually. Like, what's the right linearity that's needed for partial f, partial z to exist? It should be this, right? If we have df of, say, h star, I don't know, what do you want me to put here? Pac-Man, say h1 star, I'll say v, comma h2, right? So I have multiplication in the first component. If that's equal to df of h1, h2 star v, and if df of h1, h2 star v is equal to df of h1, h2 star v, I think, maybe I should put w over here just to be kind of cute. I think this condition, it will tell me that partial f, partial z exists. And I think this one down here will tell me that partial f, partial w exists. Again, I've suppressed the points here, but and if they both exist, I think that the differential is right alinear in sort of the total sense. Like, there's an A multiplication. So what's the A multiplication on A cross A, by the way? Think about A cross A as itself as an algebra. I think I called it like A prime or something before, Think about A prime as a new algebra, A cross A. And if you want to talk about, is there a way to multiply A on here? Well, there is, right? You just do A times XY is AX, AY. Sorry, I'm not writing stars. But with respect to that notion of multiplication, I think this ties, what I'm trying to say, Audric, is that this ties into the discussion of differentiability on the I have a discussion of what it means for a function on the extension algebra to be a-differentiable. And I think this ties into that same can of worms. There's really nothing. It all worked. Was the thing that makes it a little bit unmemorable. All right, so great. Just in summary, I think we're good on the forward direction. Like I think it's going to work. No.
Yeah, forward direction looks promising.
So let us go the other way. Make it go through the other direction. So that happens. So let's see here. Oopsie. I'll regret erasing something, I'm sure. Alright, so
Now we're going back.
I'm trying to go back, yeah.
So, given partial p, partial y of xy is equal to partial q, partial x, xy. That implies gradient f equal to pq. Yeah.
Right, so by theorem 16.92, there exists f, right?
Yeah.
Such that partial f, partial x equal to p, and partial f, partial y equal to q, right? On the omega. Now, what are we trying to show?
Well, if we have the supposition we know that f is twice differentiable, that an f would be twice differentiable.
Oh, yeah, I'm sorry. I'm kind of assuming what we're trying to prove here, aren't I? Which is this.
Yeah.
But just hang with me for a second here. Let me show you why it's interesting to prove this. So, the thing I haven't quite made clear is I claim that this solves C star. So let me explain why that is briefly here. So why do we set f equal to a constant? Why does it solve? Well, let's just say this. If fxy equals to a constant, then there exists phi such that, some subset of the reals goes to the reals locally solves, the level equation, which is this one. Namely, f of x comma phi x equals to a constant, right?
I'm rewriting, sorry.
You're fine. So then, if we go back to the star, right? So in this notation, so essentially y equals to phi of x, solve star is the claim. If you want to go back to the world of functions instead of equations. So I'm going to talk about the function proof. So All right. So essentially what we got to do is just differentiate this equation here with respect to x. All right. Differentiate with respect to x, we got partial f. And it's even better to, instead of writing x here, to write p maybe. Well, I'll finally leave all the x. Fine. Partial f, partial x. And then partial x, because that's the component there. Plus partial f, partial y. Partial v, partial x. I should say dx really. Curses. Let me say dx. D phi dx. Sorry, this is the chain rule. I need a name for this thing, ghost. So d ghost dx equals to this by the chain rule, but it's also equal to 0 because the derivative of the constant is 0, right? And to be more explicit here, this is partial f, partial x evaluated at x comma phi x, and this is partial f, partial y evaluated at x comma phi x, to be like totally honest about the chain rule. So we have to evaluate at the inside function. But notice the condition, notice what we've assumed about big F. Partial f, partial x is p, partial f, partial y is q. So what this is p of x comma phi x plus q of x comma phi x times d phi dx equals to 0. But that I just wrote is exactly what's needed to solve star.
Yeah.
When we put y equal to phi of x, it solves the equation. Now there's another way to understand this, if you don't want to run through the this theorem I used right here. This then is, I'm using what's called the implicit function theorem, for what it's worth. And that actually only holds if a particular condition is met on the function, which is probably met here because of where the function comes from and such. But anyway, without digressing into that momentarily, if you just have f of xy equals to a constant, right? You take the total differential of this equation, and that gives you df equals to the total differential of a constant. Of course, the total differential of a constant is 0. The total differential of f here is partial f, partial x dx plus partial f, partial y dy equals to 0, right? But remember, partial f, partial x is p, and partial f, partial y is q. So you get that. And that is why f equals to a constant solves the differential equation p dx plus q dy equal to 0. I actually kind of prefer what's written here because it doesn't presuppose a function viewpoint, right? Like this star equation, it makes x and y not play in the same level field. You know, like x and y are conceptually different. Y is the dependent variable, x is the independent variable. In this nomenclature, x and y, whichever, they're just, you know, two variables, the Cartesian coordinates of the plane. So, I don't know, I really like this way of thinking, but anyway. Okay, so all of that said, you see the value of finding the potential function, right? Because if we can find f such that the gradient of f is p comma q, then the level curves of that potential function are solutions to the you know, the given differential equation, which is of course called an exact equation in this context. Okay, so what do we need to do? We need to prove the other direction of theorem 16.9.2. That direction. So why is it that the closed condition implies the existence of a potential function? Right? Can I erase this stuff?
Yeah, and my intuition says that, well, I don't know, like, it just makes sense. It's such a weird question. Like, if exactness is met, you know, you have to have a function in which,
Stupid clickety clickety. So the answer is given on page 859, like the proof of theorem 6.9 we want to look at. It's over there. It is not obvious. I think I have reached the time for second coffee. So did you have a productive week otherwise?
in what sense?
Like, in the running sense, or?
Yeah, I finally can start running next week.
Ah.
Trust me, 2 hours on a bike is not fun.
Oh, I see. So you're still in recuperation from the...
Yeah, I think I'm fine. I just see, like I said, my teammates had bad injuries at the end of the season, and he doesn't want to make the same mistake again, because they were chronic injuries, and like in the world of athletics, especially that type of athletics where you have to use the same muscle over and over again, or muscular system, chronic injuries are going to happen. But yeah. My friends are quite worried about me. I'll tell you more about that at dinner. She guys called me about like running athletic problems. I'm just, oh yeah, that's true. But she's like, what? This happens? I was like, oh yeah, 100%. She was like, I thought this just happened with Jim. No, all of us.
It's funny.
Yeah. Because I just told her at the base level we're all destroying our bodies. That is the thing that people don't understand about like Olympic athletes. Like, no, we're destroying our bodies. It's in the pursuit of perfection.
Let's see here. So,
see,
on page
this is, you're right, this is not, like, it is, but it's not. Like, that's not how, well, I guess, I didn't, yeah, no, it makes sense. I mean, because, I mean, essentially, like, that's what you're saying, that if you have a partial, if you have two equations that equal each other, taking the partial of the subsequent variable, that means that your assumption is that there exists an f. So how would you prove that? You'd say that you'd have to take the integral of both and then add them together. But this line, this vertical line and the horizontal line thing, I don't know. I can't really understand that. I don't understand that. Oh, but it makes sense why you would add them because they're both in respect of different variables. Therefore, if you add them together, you get both variables back.
Mm-hmm.
And then I get why you'd integrate. I don't get the visualization part at all. And then adding this together, you get a p and a q.
Yeah. See, let's write it down here. Try to work through it.
Yeah. No.
So we assume this condition.
Yeah.
Then we write down our alleged potential function, f of x comma y, equal to what? The integral from x. So we also pick a point, right?
Yeah.
So this is, I think he says for simplicity he's going to assume that omega is rectangular, right?
Yeah.
So you pick that point, x naught, y naught, let's call it the origin, and you integrate from the x coordinate of the origin, x naught, to x. The p function at u comma y naught du plus what? Plus the integral from the y coordinate of the origin to y, q of
U naught to x naught to v, right?
but it has x here, not x naught. X comma.
Ooh.
See, that's funny. Why does it have? I wonder if that's a typo. Nope. Nope, it's not. X comma v.
Oh, that's weird.
The question is which came first. There's an asymmetry in the role of x and y here in this argument. Because he goes first the horizontal part and then the vertical part. So like, I draw it over here. So we start at x naught, y naught. And then he goes over here to this point, which is, x comma y naught. And then goes up here finally to the point xy. Right? Just to unpack what that formula is doing, let's see here. So like this, we have, if you look at this line segment, we have equation what? X equals to t, right? Y equals to y naught. X naught less than or equal to t less than or equal to x. I've misused the x notation here a little bit. Sorry about that. If you like, I can reformulate that into a vector kind of thing. So like the parameterization, this is, parameterization of that is RT is, what is it? It's t, comma, y naught. X naught less than or equal to t, less than or equal to x. That's that line segment, right? We call it R1. And then over here, R2, I'll use t again. Well, it's fixed at x. So x and comma t. But this time, y naught less than or equal to t, less than or equal to y. Okay. So if you look at dr2, dt, you got 0, 1. If you look at dr1 dt, you got 1, 0. So, and so in all honesty, what we're really looking at here is the line integral of pq dot dr, or along, you know, let's say c1, and this is the line integral along c2 of p comma q dot dr, right? In the usual notation for line integrals in the plane. And I'm saying that, you know, this is c1 and this is c2 for what it's worth. I mean, that's where this formula is coming from. I guess. Now, I guess the logic here in Salas and Hilly is, this is, you know, chapter 16, and I think in chapter 18, he finally, they get around to proving things about, I mean, chapter 18 is line integrals and so forth. So they may not yet have, at this point in the text, the theorems about like path independence for conservative vector fields. But if we do know that, then like a couple different ways to go here. The one way is that the value of f so defined is unique because there is just one line segment
that goes from
that goes horizontally over to the x component and then up vertically.
Still okay for my pizza?
Oh yeah. Well, did you ask Matthew if it's okay?
Oh, he's just muted, he's gonna be loud with the blend.
Oh, I think we'll be okay. Matthew's like, I just need Mommy's pizza. I just need it. And he's sick, feeling sick the other day. He's like, I would feel better if I had some of Mommy's pizza.
So we're calling, are we calling R or like a combination of R1 and R2? Here's a vector. It's a vector.
That's just notation. dr, that's notation for line integral. I mean, technically speaking, the definition of line integral, you give it a curve, integrate a vector field, you find a parameterization of the curve, you evaluate the vector field at the parameterization, multiply it by the velocity, take the dot product with the velocity, integrate that over the parameter domain. That gives you the value of the line integral. And you can prove that that's independent of the choice of parameterization.
Pretty sure I remember that.
But of course, the parameterization has to be consistent with the orientation of the curve. The line integral is an oriented integral.
I think.
Now, I think all that technology is not needed here for this argument because, well, this is a specific line that's, this is the reason choosing a rectangular domain makes this life easier. The path independence result is something that, I mean, it's stated for like an open set, an open connected set, I think. So, there, if you made this, my point is if you were working in a more general, like not just a rectangle but something else, you could still make this the, you could still define the potential like this. But then the trouble is, if you're in a more exotic like set, you don't know that the L is inside the set, you know? Like if you're, the set that you have